right here, in example D6, this asymmetric frame with asymmetric loading, we've gotten all our equilibrium equations written, represented here in matrix form. That's the stiffness matrix times our vector of unknown displacements, generally speaking, plus the fixed end force effects, and then equal the applied nodal or joint force effects, which in this case are 0. And again, in the matrix form, we have this written out that our B, C, and D stood for our EK theta B, EK theta C, and EK delta down here. And then we take the fixed end force effects, turn them over to the other side. These are all fixed end moments, and so they have units of kilonewton meters. Now you can choose to solve these by hand, or as I did, go to a mathematical solver. I went to Excel to do the inversion. Sometimes you have to be careful with the results that you get out of Excel. Always want to do some double checking on the accuracy of their inversion techniques. When you do this though, what I get for B, C, and D, remember that's still, again, these EK theta or EK delta terms are these values. 0.872, where the 72 is repeating in the decimal, minus 1.309 for EK theta C, the 09 is repeating, and then we, oddly enough, get exactly the same numerical value for EK delta. There's no reason to have believed this. One of them was a rotation, one of them is a sway term. It's a happenstance kind of thing, and it's not the first thing that is an unusual and surprising numerical result in this particular example. So we want to, explore to see is there something goofy about our data entry in our solver routine. Have we made a mistake mathematically along the way? And one of the ways to figure out whether you've made mistakes is just go calculate the member in moments and see if you get the appropriate relationships when you do that. So along the way here, let's keep in mind also a big picture here, that we anticipated the rotation at B would be clockwise. It has turned out to be that way, that the rotation at C would be counterclockwise. Sorry, yeah, that's right, clockwise there and counterclockwise here, negative and positive. That's what those signs mean for those two. So that's good. And we also had argued that although the initial guess was a sway to the right, and we went and looked at that moment diagram that was consistent with that, it didn't make any sense. And so we tried it a couple of different ways and finally got ourselves to the viewpoint that actually this structure would sway towards the more flexible side of the system. And that's what this negative value on the delta term is telling us, is that when we set everything up with delta going to the right positive, we ended up with a negative value. It means it's really going to the left. And that's kind of an interesting result that we'll begin to peel apart here a little bit more. So let's go get those member end moments and see what might be really going on. Right, you of course take these values, substitute them into our individual member end moment equations, and we get at the AN a clockwise 21.8. Right, so I'm going to sort of repeat these things down on our free body diagrams of the individual members as we go. So there's our 21.8, the way it physically is acting. At the top, a clockwise 30.5. That means from a shear standpoint, we got to have a force couple for the shears that are going in the opposite direction, and of course they're 6 meters apart. So 30.5 plus the 21.8 equals 52.3. Divide by 6, we get about an 8.72 for those. We don't have the axial forces yet, but that's alright. Okay, and then we turn the corner to BC and we have equal opposite. That's good. That's supposed to be that way. That wasn't just written down that way, that was calculated that way. That gives us a little bit more confidence that our values are correct. There's your 80 kilonewton load on the member, and then at the far end we get a clockwise 26.2. And then let's go find out what the shears are here. 30.5 plus the 80 times the 2 meters is 190.5 minus the 26.2 and then divide by 5. That's the equilibrium that's going on, and we get a shear value here of 32.9, which of course means that our axial force down here at the lower left is 32.9 down there, right? And then let's go get then the other one, which is supposed to be, of course, the difference between that and 80, so that would be 47.1, but let's just do the moment at the other end and see what happens. 80 times 3 plus 26.2 minus the 30.5, and then divide the whole thing by 5, and sure enough we get 47.1. So that's good. That will be our axial force down at the bottom of that column. You're not supposed to see that moment diagram yet. And then let's get our moments on here. We got at the top of CD we have 26.2 going in the opposite direction. We had the surprising result of 0 here. Right now, if this is going to really work out right, then the shear top of this column becomes an axial force in the beam, and then that would be 8.72. Let's see what we get. 8.72 times 3 for the moment arm for that one, 3 meters, and then minus the 26.2 and a little rounding error there. Sure enough, we get 0 down there. So at the very least, we have a compatible set of internal force effects all the way through the system, and that makes me feel happy. Even though at the fixed end that we have at this lower right, we said that we ended up with 0 moment. That's a little bit of a surprise, but at least it looks like we have internally consistent results. Right? So the moment diagram then that goes with the left-hand beam being the way, or left-hand column that is, being what it is. There's your 21.8 going to one side, reverse curvature, 26.2 that's not 26.2, that is 30.5 and 30.5. And then the 26.2 is at the right-hand side. We got the other column from 0 to 26.2, but we don't know what the positive maximum moment is going to be. We can then come over to here, cut just to the right of the load, and we'd have 47.1 times 2 meters, and then subtract off our 26.2, and roughly we get another surprise, almost exactly 68. Right at the peak of that, right? And this moment diagram is entirely consistent with the deflected shape that we've drawn, and so we've got a lot of consistency here, even though we have a 0 moment. So in the final reflection phase of this example, we'll talk a little bit more about some of these surprising results, but it sure does seem as though we have something that makes a lot of sense overall.